In this video, we'll be deriving the conservation of energy equation for a control volume undergoing steady uniform flow, and we'll do so using Reynolds transport theorem. And recall, Reynolds transport theorem is a means by which we can link a Lagrangian to Eulerian fluid analysis approach. So because we have to relate these two approaches, we first have to review the conservation of energy for a closed system before we can proceed. So if I have some closed system at state 1, and it has some corresponding total energy at that state, and it undergoes a process, thereby changing states to what we'll call final state 2, which has a corresponding total energy at state 2, that change in state and that change in total energy is a result of energy transfer. And we can have two different types of energy transfer, the first of which is heat transfer. So we can have heat transfer in or out of the system from state 1 to state 2, and we can have work in or out of the system from state 1 to state 2. So if I write this mathematically, we get that the change in the total energy of our system is equal to the heat transfer from state 1 to state 2 minus the work from state 1 to state 2, and that's our total energy transfer. Now, if we had values for heat transfer for work, the signs that we would use when we input those values into this equation would come from our mnemonic HIP to win. Heat in is positive and work in is negative. So let's write this in differential format and say that my change in the total energy of my system is equal to the inexact derivative of my heat transfer minus the inexact derivative of the work. And those are inexact derivatives because they're path dependent, and we may not know the path. Now, if I want to know how those change with respect to time, I simply take the time derivative of each one of the elements of that equation. So let's do that, and that gives us the conservation of energy for a closed system, which states that the change in the total energy of the system with respect to the change in time is equal to the rate of heat transfer minus the rate of work. And that rate of work is also referred to as power. So now let's derive conservation of energy for control volume using Reynolds transport theorem. Let's review Reynolds transport theorem first and recall that it links closed system properties to control volume properties through the time rate of change of some extensive property B. B is any extensive property. Recall that an extensive property is a property that relies upon the, or is dependent upon the mass or size of the system. If I want to make it intensive and thereby independent of the mass or size of the system, I simply divide that extensive property, divide it by the mass, and that gives me a specific property, which by definition is intensive. So let's pull up Reynolds transport theorem. This is equation 3.11, and this is in your book, and you should have seen this if you watched the video for the development of conservation of linear momentum and the conservation of mass for control volumes. But let's just review it one more time in plain English to make sure we all understand what we're talking about. On the left-hand side of the equation, it states that the rate of change of some extensive property in my system is equal to the rate of change of that extensive property in my control volume plus the net flow rate of that extensive property exiting my control volume through the control surface or across the control surface, and that includes what's going in and what's going out, and that's also referred to as flux. Alright, so finally, let's apply Reynolds transport theorem to energy. We're going to do it the same way we did conservation of mass, the same way we did conservation of linear momentum. So in Reynolds transport theorem, I'm going to let my extensive property be total energy. So if my specific property is the extensive property divided by my mass, then it's my total energy divided by my mass, which gives me specific total energy. So let's go back to Reynolds transport theorem. Everywhere I had a lowercase b, we're going to put specific total energy, and on the left-hand side where I had capital B, we're going to replace that with the total energy of the system. Now recall from a closed system that the change in the total energy of my system with respect to the change in time is equal to the heat transfer, the rate of heat transfer into the system minus the rate of work into the system. Now let's look at the first term on the right-hand side of the equation, this time derivative of an integral, which can be intimidating, but really just look at it in simple terms and realize that the density is the mass per unit volume. So if I have mass times a specific property, that gives me a extensive property, in this case total energy, and that's per unit volume. So if I take the closed integral over the entire volume, that gives me the total energy in the control volume, and then I'm going to take the time rate of change of that. So let's write it that way so it's a little bit easier to see. And so that term becomes the change in the total energy in my control volume with respect to the change in time. So now we have Reynolds transport theorem in this format. Let's start applying our assumptions. the first assumption we're going to make is that it's uniform flow at the inlets and exits. And this allows us to simplify that integral over the control surface with that dot product, because what that means is basically we're taking the average values of the velocities going in. We're saying the velocity going in, the velocity going out, that they're perpendicular to the control surface, which means they're parallel to the outward normals of that control surface. So if we look at the dot product for the fluid that's going in, that gives us a cosine angle of 180, which becomes -1, and going out, that gives us a cosine angle of 0 between the velocity vector and the outward normal, which gives us +1. So we can replace that integral with summations. And so on the right-hand side, I've replaced that integral with the summation of the mass flow rates times the specific total energy at each of the exits, and there could be multiple exits, that's why we have a summation, minus the mass flow rate times the specific total energy for each one of the inlets. Now let's assume steady flow. And recall, if we're assuming steady flow, that means the control volume and the properties therein are not changing with respect to time. So that means that derivative of the total energy in the control volume with respect to time doesn't change. This means it's equal to 0. So that term just cancels right out. So this is now what we've determined for our Reynolds transport theorem using uniform and steady flow. Now let's recall the fact that specific total energy is equal to the specific internal energy plus the specific kinetic energy plus the specific potential energy. And we know that the specific kinetic energy and the specific potential energy are 1/2 times the velocity squared and the acceleration due to gravity times the height above the reference datum, respectively. So we're going to take that, we're going to insert it into the equation at the left, and this is our result. So it's a little bit expanded. And so we're going to hold off here. I first want to expound upon that power term, that rate of work, because that rate of work is not just one value. It includes different types of work and the rates of each one of those. So let's pause for a moment. Let's expand upon that, and then we'll come back, we'll recombine it, and we'll finish up deriving the first law of thermodynamics for control volume. So looking at the total power term in the control volume approach for steady uniform flow, we see that that total power term is comprised of the rate of shaft work, the rate of boundary work, and the rate of flow work. So let's look at each one of those individually. So the rate of shaft work is the power associated with a rotating shaft, and that could be power required to rotate a shaft in a compressor or a pump, or the power generated by a rotating shaft as in a turbine. And the equation for this is in your book, and it's equation 1.32, and it simply states that the power associated with rotating shaft work is equal to the shaft work divided by time, which gives us 2 pi times the speed of rotation times the torque. Now let's look at the boundary, the rate of boundary work, and let's do so by looking first at what boundary work is. Boundary work is the integral from state 1 to state 2. In this case, it's an open system, so we're going to say from the inlet to the exit, of the pressure times the change in volume. Now, we can have special cases where we assume pressure is constant, but let's just keep it generic and say we don't know how pressure varies with change in volume, so we'll keep it as a variable inside the integral. So if I want to find the time rate of change of that, I'm going to take the time rate of change, the derivative of the resultant integral. Well, again, we assume steady flow, so we're saying that in the control volume, nothing changes with respect to time, so that becomes 0. So in a control volume with steady uniform flow, my rate of boundary work is 0 because the boundary work is 0. Now let's look at the rate of flow work required to move a mass of fluid across the control surface, or into the control volume, or out of the control volume across the control surface. So let's look at some inlet, and let me draw a portion of the control volume. In this case, it would be the control surface, where I'm going to push fluid into the control volume. And I have some volume of fluid. Now, in order to move that fluid, I'm going to have to apply some force to make it travel some distance. Okay, now recall the basic definition of work, which is force times the distance. We can therefore say that the work of the flow, the work required to generate the flow, is equal to the force required to move that volume of fluid times the distance we moved it. Well, we don't really apply force to a fluid, it's more of a pressure. So let's break that force term up into this cross-sectional area and then the distributed pressure. That distributed force has a pressure over that area. So let's say that it's the pressure times the area times that distance x it had to travel. Well, that cross-sectional area times that distance x, well, that's equal to volume. So that means our flow work is equal to the pressure times the volume. And realizing that volume can also be written as specific volume times mass. Let's do that. Let's pull that mass term out and replace volume with specific volume. And then if we took the time rate of change of that to figure out what the rate of flow work is, it would be the rate of flow work is equal to the mass flow rate times the pressure times the specific volume. And those wouldn't change with time, those being the pressure and the specific volume, because we assume steady uniform flow. So let's substitute those all back together. Let's recombine that into our total power. Okay, and note that there is no boundary rate of boundary work. We have the rate of shaft work, and then we have a summation of the flow work at the exits minus a summation of the flow work at the inlets, because there could be multiple exits and multiple inlets, and so we want to account for all those. And realize where the sign comes from. It comes from our mnemonic hip to win. Work in is negative, so the flow work at the inlets is negative, and the flow work at the exits is positive. All right, let's tie it all back together. So on the top left-hand side, I have that expanded version of the power, and below that I have where we'd stopped off in our derivation of the conservation of energy equation for control volume undergoing steady uniform flow. Now I'm going to take this expanded power, and I'm going to input this into the equations. That's all we're going to do. And then I'm going to remove these parentheses and just distribute this negative sign throughout just to clean this up a little bit. So that's the only thing that's going to happen now when I hit the button. So now you can see that I have like summations on the left-hand side and the right-hand side of my equation. So I'm going to take the summation of the mass flow rate at the exit times the pressure at each exit times the specific volume at each exit, and I'm going to put those over on the right-hand side of the equation under this summation, and obviously pulling the mass flow rate at each exit out of that term. I'm going to do the same thing for the inlet. Okay, so now you notice on the left-hand side, the power term that remains, the rate of work that remains, is only shaft work. The flow work is incorporated in the summation on the right-hand side. Okay, and that's going to be important. And I put it in the order that I did so you can hopefully see something. I have my specific internal energy plus the pressure times the specific volume. And I hope you recognize that that is a property that we've discussed earlier, a thermodynamic property called enthalpy, which is a convenience property that was generated specifically for this purpose. So I can replace that with enthalpy, something that I could look up in a table if I needed to, if I had two other thermodynamic properties by which I could fix a state. So we have enthalpy at the exits and enthalpy at the inlets. So let's replace those terms with enthalpy in our equation, and then let's let the power term on the left-hand side, let's rename that the power from the inlet to the exit, realizing, however, that is only shaft work. Okay, but we're going to do this just to make it generic for a control volume for an open system. And there we have it. We finally get to the first law of thermodynamics for a control volume undergoing steady uniform flow. And it's the heat transfer, the rate of heat transfer from the inlet to the exit minus the rate of shaft work from the inlet to the exit minus the summation of the mass flow times the enthalpy plus kinetic energy, specific kinetic energy plus specific potential energy. And that's for the exits and for each one of the inlets. And that's equation 3.41. Now that's the more general form. Obviously it's specific to the fact that it's steady uniform flow and a control volume, so an open system. But let's narrow it down even further to another equation that's also on your reference data card. And that's a special case that we have only one inlet and only one exit. And that actually occurs more frequently than you might think. And if that's the case, thinking back to conservation of mass, if I only have one inlet and one exit, whatever's flowing in has to flow out due to conservation of mass. So that means the mass flow rate in and the mass flow rate out are equal, so I can just call that the mass flow rate. I'm going to pull that out, and obviously we get rid of the summations because there's only one inlet, one exit, and we're going to group like terms, and we get this equation for the first law of thermodynamics for a control volume undergoing steady uniform flow with one inlet, one exit. So very specific usage for this equation. This is equation 3.42. Now both of these equations are concerned with the thermal aspects of our system. We may be concerned with mechanical aspects of our system, and we'll cover that in the next video. But let's quickly do a example problem. And this is example 3.7 from your text, and if you want to read all the particulars, you can pause the video. I'm going to go ahead and work the analysis. So what we know is we have steam and water, and they're mixing to provide preheated water to some other thermal fluid system, and we're only going to look at this mixing process. So what we want to find is the rate of heat transfer in kilowatts associated with this mixing chamber. So if I do my diagram and data, I see that I have two inlets and one exit. And I have been given the mass flow rate at each of those inlets and exits and the corresponding enthalpy for the inlets and exits. Now, I have some rate of heat transfer, and I don't know whether it's in or out. So I'm leaving it a question mark, and I have it going in or out. And we'll see what number we get at the end, and then we'll ask ourselves, does that make sense? So let's make some assumptions. We're going to assume the mixing process occurs at steady flow. Now, this is obviously not true in a real system, but we'll find that this assumption is going to give us pretty close to a realistic answer and allows us to do the analysis. We're going to assume all flows are uniform, and we're going to neglect the kinetic and potential energy effects for now. So that the problem told us to neglect those. We can probably look and say the mass flow rate is so low that that's probably reasonable that we can neglect kinetic energy, that the velocities aren't such that great enough that it would make a huge difference, and the potential energy effects we're just going to neglect. We're not going to say that we're changing elevation in or out of the system. So let's do the analysis. I threw the diagram and data up there in the top right so we can refer back to it as necessary. But if I want to find the rate of heat transfer, that can be determined from the first law of thermo for steady flow in a control volume using equation 3.41, which we just derived. All right, so go with what you know. We're going to start off with that governing equation, and we just derived it. And let's take a look at our assumptions. Now, our assumptions in the problem said we can neglect the effects of kinetic and potential energy. So let's get rid of those terms right now. Boom, they're gone. They're out of the equation. We also note that there is no shaft. There's no turning shaft. There's no turbine. There's no compressor. There's no pump. So that means our rate of shaft work is also zero, gone. So that simplifies the equation considerably. So what we have is the rate of heat transfer from the inlet to the exit is the mass flow rate at the exit 3 times the enthalpy at 3. Now, we have two inlets, so we have to subtract both of them, minus the mass flow rate going in at 1 times the enthalpy at 1, minus the mass flow rate at 2 times the enthalpy at 2. And we were given each of those values, so now we simply substitute those values into our equation. And let's take a look at the units here, and we see that the kilograms, they cancel out, which is good. That's what we want. Okay, and then we were left with kilojoules per second, and realizing that a kilojoule per second is equal to a kilowatt, which is our unit of power or rate of energy transfer, which is what we want. It's perfect. Our numbers are good to go as they are, and what we compute is that our rate of heat transfer from our inlet to the exit is equal to negative 533.3 kilowatts. So we have to ask ourselves, does that make sense? Using our mnemonic, our work, our heat in is positive, HIP, heat in is positive, we get a negative number, which means it's heat out, right? So does that make sense? Well, it's not adiabatic, it's not insulated, and we have steam coming in, which is obviously hotter than room temperature. If we assume that it's atmospheric pressure, standard atmosphere, standard temperature outside, it makes sense that the heat would transfer out, that we'd be losing heat to the environment. So at this stage, we would say, yeah, this answer does make sense. Okay, if you have any questions, feel free to talk to your instructor, work some sample problems, and make sure you check out the next video where we'll talk about the mechanical applications and the variation of conservation of energy for a control volume.